Next lecture is given by Professor Vitório Pereira from here. So his title is on the holonomy group of algebraic curves invariant by holomorphic foliation.
Thank you. Primeiro eu queria dizer que é uma satisfação estar aqui participando da conferência em homenagem ao professor Camacho, que foi meu orientador. E, bom, so the problem is the following. Let's see be a smooth algebraic curve contained in projective variety M.
Sorry, you like more?
It's bigger? Okay. And if we have a foliation, a holomorphic foliation of M that leaves C invariant, most of dynamics of F, if F is a foliation, the dynamics of F around C, near C, is essentially determined by the holonomy of C. The holonomy, as everybody knows, is just a representation of the fundamental group of C minus the singularities of F on P to the diffeomorphism of a transversal. Then on this work, which is a joint work with Alcides, we are interested in knowing what can be said, for instance, what kind of diffeomorphism groups, what kind of representations can appear. As is well known, this is put on this generality is a quite hard question, so we are going to stick to a simpler case, and instead of looking to the whole holonomy, we are going to look just for instance, to the linear part first. So here I can, for instance, compose with the derivative and get a map on GLMC. Again, if we just give, so if given a phi of P1 of C minus a point set P to GLMC, we can ask if there exists a foliation with singular set equal to P and with linear holonomy given by phi. In general, put in this form is not true. For instance, if we take P an empty set and C containing P2, then the Camacho-Alcides index theorem says that if F is a foliation leaving C invariant, we say that we know that implies that the singular set of F intersects P and C. So what can we hope to get? We can, for instance, think on a weaker form of this realization problem. We just want, for instance, that if I give a homomorphism like this, I can ask if there exists a foliation. This is the question. Exists F such that such that the singular set of F contains P, and the singularities that on the points where P, the points of P which are not contained on sing F have, for instance, trivial linear holonomy. That's the meaning of this diagram. So, and in fact, this kind of result was already, had been proved by Paulo Sade, I think in 1907. Paulo Sade proved that when C, it's a curve on P2, and if phi is an homomorphism on GL1, that's C star, then there exists a foliation such that making this diagram commute. And we proposed to establish this result when M is a general projective variety in a kind of generalization of this result. So our first result is the following theorem. 1 is that given phi P1 of C minus P and C, of course here C is contained in M and P contained in C is a point set. There exists F, a foliation of M such that the diagram 1 commutes.
Is map star is non-canonical?
Sorry?
The map star.
Yeah, it's non-canonical, but in fact it would be safer to say that we are taking a transversal and we are doing something to the, for instance, we can think of C here and take a transversal. We fix the transversal and we should say that this is an homomorphism here.
No, I mean a homotopic class of C minus P does not induce in a natural way a homotopic class if you delete more points. It's the other way. The map is the other way.
Oh, like this.
Yeah, that's a canonical map.
Yeah, you're right, thank you. Thank you. Of course. Thank you. Okay, so I would like first to discuss the ideas of the proof of these results. And it's a kind of algebraic nonsense, no? The first thing is we have to equate these, no? We have to translate this into an algebraic form that we can tackle. So the idea is to consider.
Excuse me, another question. So does this mean that the holonomy around the singular points, the additional singular points, is the identity?
No. This just means that the holonomy around the other singular points are tangent to the identity.
So it's not like that. See, because that means the kernel of the map, the kernel of that map is sending the loops which go around the additional singularities to 0.
Yeah, but this is just the linear part of the holonomy. So the points here, we have the points on P, and here we have these other extra singularities. I'm just saying that the holonomy here is tangent to the identity. Okay? So we are going to consider theta MC, the sheaf of vector fields on M tangent to C. And we have this, we are, if we look for a foliation, if F is a foliation, leaving C invariant, then we can see F as a section of this tangent sheaf twisted by a line bundle, which we will call the cotangent bundle of F. Okay? So the idea is to come from this algebraic object, and from this object derive some things that permits us to compute the linear holonomy. But if we do local calculations, we see that to compute the linear holonomy is essentially to compute, we can divide in two steps. First, we look for the image of we look for the image of F on a sheaf like this, which is just the cokernel of this. It's just the cokernel of this inclusion. No? So NMC is nothing more than the cokernel. And if you look how the sections here are, and we try to compute from this data the linear holonomy, we can see that the linear holonomy of F will be completely determined by the image of F here, no? In other words, with the note by C, from H0, theta MC, tensor T star F, to H0, M, N, MC, 1, tensor T star F. Then the linear holonomy of C just depends, do not depend on all this information on the section here, but depend just on the image under this map. So we reduce our problem to a construction of a section here. But how this sheaf look like? First of all, we remark that this exact sequence induces a natural structure of OC sheaf on NMC. So NMC 1 is supported on C. And how the sections of NMC look like? Well, we have first to know how the sections of theta MC looks like. So locally, our curve C can be just described if I consider local coordinates here x, and on the transversal y1, y2, and so on, ym. Then we can see that theta MC is something like this. In a point, if P do not belong to C, it's just the theta M. And if P belongs to C, then theta MC is something like, is generated by ddx and y ddy. Okay? So, a section here will be just a kind of vector field which will locally will look like this. Will be ax ddx plus yj byjx And then looking at this form and seeing how this change, we can, it's not very hard to see that NMC as an OC module, OC sheaf, is isomorphic to NCC, where NC is the total space of the normal bundle of C on M. And also this section naturally induces a meromorphic connection, if you want, or a linear differential equation over C with coefficients on the normal bundle. Well, not precisely that, but which is just you have just to define something like this. You define a matrix B, which will be Byjx over A of X. And then the differential equation will be something like this. Okay? So, what's the point? The point is that now we have reduced our problem to construct. We have two problems, of course. We have a lifting problem. We have to lift this map from here to here, and we have to construct a map here that has the linear holonomy that we want. And this construction, well, the lifting is not really a problem since we have Soares vanishing theorem, because if L is ample, it's an ample line bundle on M, and K is a sufficient large integer, then C, this map from M, theta and C. I can put C here now since it's supported on C. This map is surjective. This is Soares vanishing theorem. Therefore, we have just to build some kind of foliation here, or a section of here. But it's nothing more than building a foliation on the total space of the normal bundle, which is kind of linear, no? So how can we do that? This is in fact quite canonical, to build a foliation on a vector bundle. We have the canonical construction. So from this remark, let's divide the ideas of proof in 3 steps. The step 1, we build a section. We build a linear foliation, let's say like that. On some rank M vector bundle. And this is just the usual process of suspension. No? How do we do this? Just a vague idea. We start with, we have this representation, no? P1 of C minus P to G and C. And how we do? We consider C tilde the universal covering of C minus P. Then we can define the foliation. We consider the trivial foliation on here. We can take the trivial foliation. the leaves are just C tilde times points. Then we use this automorphism, this representation to glue. So if alpha from P, C minus P, to the automorphism of C tilde is the group of covariant transformations, then we can consider an action on XV here, which will be just alpha X phi alpha X, alpha gamma X to phi gamma V, and we just take the quotient of the trivial foliation by this map. Then we have defined something on a vector bundle on C tilde on C minus P, a foliation which has the linear holonomy that we want, and we just we can complete the wholes by constructing local models which are just linear differential equations. We have just to take the log of the holonomy around these paths. Okay? So with this we have just constructed a foliation on a vector bundle E, but it's almost what we want, but we want something like this on the normal bundle. So the step 2 is just that the only bimeromorphic invariants of vector bundles is the rank. We can take a bimeromorphism between NC and E. So we have that object defined over there, and we can pull back that object to NC. Therefore, so let's call this object, so we have construct here age, foliation of E. So we have age here. This is this map over the fibers is linear. No, it's a bimeromorphic equivalence between these two rank M vector bundles. And then we have age here. We just pull back age. Well, this is not very good notation. No? And then we have construct a foliation on NC. But what is this foliation? We can interpret this G as something like G will be a section over the total space of the normal bundle with coefficients on theta and C. Oh, better than that. We can here, we are ready to interpret this section as just H0 of C and NC C tensor some line bundle. Let's just call, well, by analogy, T star of G, or maybe LG. Okay? If we look locally what we have constructed here, we see that this can be expressed in this form. When I do the pullback, will appear poles, but after multiplying by a function, well, not by a function, but after locally killing the poles, we obtain something that will have this aspect. Well, but now we have a problem. We have constructed something over C that, and with a line bundle over C, which we do not have control. We want something with this line bundle. In the case we want something with the line bundle L tensor K. No? But here I have constructed something with this. So what can we do? This is just the step 3 now, the final step. is just to correct this line bundle. Oh, observe that here I have enlarged the singular set. This bimeromorphism, there are fibers where it's not defined, and the tendency is that over these fibers we will obtain singularities, but there are singularities that outside a small neighborhood, on a small neighborhood of it, you have no holonomy by the construction. So here, in this step 2, we have singularities. So to solve this problem, we will introduce more singularities. So this is step 3. And what we have to do, we just look for this. We look for L tensor K, which is the target. Tensor the dual of this bundle. But if K is large enough, we have that Riemann-Roch implies that exists F in H0 C L tensor K times LG star. And if I get some F like this, then we will obtain that F tensor G will be a section of H0 C NMC 1, since this bundle is just isomorphic to NMC tensor L tensor K. Okay? But this is just the information around C that we need to compute the linear holonomy. And this has precisely the linear holonomy that we want. So we can use the surjectivity of this map to obtain foliations on M, which has the linear holonomy that we wanted. So this is sufficient to establish theorem 1. Okay? But the point now is that we would like to say something more about these maps, something more about the original problem, that where we were dealing with the group of diffeomorphism here. So we can hope that we could just erase GLMC here and consider the group of Kf jets of diff CM. We could ask if this result is true on this context. Well, we believe it's true, but we have a proof which is analogous to this one in the following case, where we are sure that it's true. And this is the theorem 2. I will just consider C a curve on a surface. Okay? And I will give this map. Then I will say that exists a foliation F on M such that the diagram, let's write it again, P1, C minus P, 2P, 2P, 2, GK, GIF, C0, phi. Here I have P1, C minus sin F, P. And here I have the diffeomorphisms of C0. Yes, like it is. I think so. Okay? And the idea is just to try to repeat the same proof. But some problems will appear, and that's why we put 2 and not M plus 1 here. And what are the obstructions? So, what are the problems that appear? Well, we are going to just to do what? We are going to define now theta MC tensor YCK. And this is just the definition of the NCK. And here we have a distinction between the two cases, is that this sheaf, it's not exactly supported on C. Outside C it's 0. Okay, but these do not carry, this exact sequence does not induce a natural structure of OC sheaf. It induces a structure of OCK sheaf. We have to look to an infinitesimal neighborhood of C. And in fact, this gave to us, and still gives to do the general case, a lot of problems, maybe by ignorance, I don't know, but in the case, let's see how we can, in the case of surface, how we can fill this gap, how we can bypass this problem. Okay? Because now we are not going to construct nothing on the kind of things that we said we do not know if it's true. For instance, we do not know if this, first of all, we have to say something. We don't know, for instance, that the case infinitesimal neighborhood on M is isomorphic to the case infinitesimal neighborhood on the normal bundle. I think it's not. And then the first thing that we stated is just that recall that the case K equal to 1, something that was fundamental to our construction, is that we have this. This is no longer true. So I don't know what's the meaning of an infinitesimal neighborhood of C on M is bimeromorphic to infinitesimal neighborhood of C on NC or on a vector. I don't know what's the meaning of that. So we are going to try to do something different on this case. So besides this problem, we have another problem that comes, for instance, on the case, for instance, that C, it's a torus. And we consider two generators. We consider the map that generated gamma 1, gamma 2, that commute generated of P1 of C. And if, for instance, if we send these to Z plus Z square, and these to Z plus Z cube, then these guys commute on G3, for instance. No? This map defines a representation of Z2 here. But, of course, these do not commute in general. And we have an extra step in this case, which is step 0. And what is step 0? On step 0, we have just to, we reconstruct a lift of this guy. In other words, I give phi on P1 C minus P 2 JK GIF C0. And then what we do, we just consider P1 C minus P union an extra point Q in order to have the following picture. If I look for, I have here C with the usual identifications, the points of P. I have here the paths, plus this path here. No, this. Let's say that the point P is just fixed here. It's just, these are the same points. And then I will take out a point Q. And then it's not very hard to see that this has the same type of homotopy than this. Well, some more petals maybe. But what this means that if I take a basis here, for instance this basis, and see these as elements of over this surface, we see that this group now is free. So I just define it on the generators. I take any lifting, and this map extends. So I have created one more singularity, but we'll have holonomy tangent to identity up to order k. Well, I'm creating singularities a lot, and no big problem. So let's write here step 1. I will just write. So step 1, what is step 1? I will construct U, a surface, a complex surface, not algebraic, carrying a foliation, which a complex surface, such that C is contained in U. So we construct a foliation there, which leaves the invariant and which has the same holonomy, which has the holonomy given by this map. But this is also already done. It has been done by Lyashenko, and essentially it's the same construction. You lift and you fill the holes. To fill the holes, you have to use a result of Pérez, Marco, and Yoccoz, but here is also well known. Okay? And now, on this step 2, what we will do, the point is that we have built this foliation, but we have no control on C or whatever. C will have just negative we will have arbitrary self-intersection, don't know nothing. But there is a theorem that will we will replace this essentially trivial statement by Brouwer's theorem. And what the Brouwer's theorem says, well, it says a lot more, but what we use from Brouwer's theorem says the following: if C squared is sufficiently small, then there exists a tubular holomorphic neighborhood. In other words, there exists a small neighborhood of C which is isomorphic to a small neighborhood of the normal of C on the normal bundle. So how do you use it? We just blow up. We have C on U, C contained on U, and have on the other side C contained on M. I want to blow up C here and here in such a way that they have at the end the same intersection number. For each blow up, the intersection number decreases by 1. But we also want that the two normal bundles are isomorphic. So we can use Brouwer's theorem and transport the foliation here to a blow up of M. Okay? So we say that we can obtain, we can blow up simultaneously C on U and C on M, such that the normal bundle of C tilde, the blow up, now I have C tilde here, and have C tilde here. The normal bundle of C tilde on U tilde is isomorphic to the normal bundle of C tilde on M tilde, and moreover, they both satisfy this bound to use Brouwer's theorem. So this foliation that I have constructed here on step 1, a foliation on an open complex surface, I can carry it to U tilde and just push it to M tilde, but not to the whole M tilde, but to a small neighborhood of C tilde on M tilde. But that's what we need, because we will have a section. So this foliation will be a section of U tilde, theta, U tilde, C tilde, to some bundle that I don't know which bundle is. No, let's say age. And we can just look to the image here. We obtain something on age 0, CK. But now I'm the real CK. This is the infinitesimal neighborhood of C tilde on M tilde. And then with coefficients on M tilde, C tilde, K, tensor LH, restricted to CK. Okay? Now that we have this section, we push it again. Well, we have the same problem. We have to do step 3. We have to make a correction because we have constructed a bundle that's just defined over a small neighborhood of C tilde. And then we have to do this same step. I will not put here Riemann-Roch, but use series vanishing theorem. Again. Okay? So with this we can, this is more or less the idea of proof of theorem 2. And to conclude, I would like just to state 2 applications. Which are the following. The first application is, there is another thing. Here I'm not really sure if we can do this, but in the previous case, in theorem 1, we can do everything for families. We don't have to restrict to one representation. We can get a family of representations which have some hypotheses like that the holonomy around the points are close to the identity, because somewhere on the construction we have to take a logarithm. And then if we take this family, we can construct a family of foliations, at least a germ of family of foliations. Okay? And with these results also, theorem 1 also for families, we can use the ideas and results of Lohay and Rebelo to prove the following theorem. It's just a generalization of part of the statements of Lohay and Rebelo, which is valid on CPN, no? And the theorem is just the following: if L is ample, then if L is ample and K is large enough, then there exists an open set, small open set, analytic open set on fol ML, which is just the projectivization, add tensor K, projectivization of H0 M Tm tensor LK, Tm or theta M, maybe theta M is more correct. There exists an open set such that every leaf is topologically dense. And we have just to repeat the steps of Lohay and Rebelo to prove this result, but paying attention that somewhere they use a kind of realization result for the line on CPN, the line at some line, and we can just adapt. They use also, for instance, Johann-Ulu's theorem, which we also know on this context, a result of Coutinho. And so, I will not say too much about this, but we can do. In fact, we have to take care of a lot of, to make sure that everything's work, we have to make a lot of lemmas, but it's essentially to generalize the behavior of foliations of degree greater than 2 on CPN, 2 foliations on a projective variety with very ample line bundle.
Should that result be for every leaf or every leaf except the compact leaf?
Every leaf. This is the result of Lohe and Rebelo.
Do you have an invariant leaf?
No.
So you cannot apply this argument you showed before about, before there was always a compact invariant leaf.
Mm-hmm.
And here no.
No, but the idea of them is just you start with a compact leaf, you prescribe the linear holonomy. In fact, you prescribe a family of linear holonomies. Then they have a result about the group. If you just destroy this compact leaf, then you obtain a pseudo group which do not have a common fixed point, and this group is ergodic, minimal on this ball, and you have to, in dimension 2, you just have to take this result for a curve with ample normal bundle. But in general, you have to do an induction trick, you have to construct foliations on ample hypersurface and try to reduce to this case. But these are the ideas of them. Okay? And the last application, because we had the theorem 1 and then we obtained this. But now from theorem 2, of course we can say much more, but I think there is a lot already said on the dynamics, on the complement of curves. And we just state a simple proposition that I couldn't find on the literature. Even in the case of CP2, maybe it's known, I don't know. And the proposition is the following, is that, so I will restrict to the case of C contained on S2, a projective surface, and I will look for M, C, L tensor K, which is just the projectivization of H0 theta MC comma of M of S theta SC tensor L tensor K. So I just consider this space, and here I can consider the subspace Sol, which is just the subset of foliations with dense, with solvable holonomy group. Then for MC Sol, L tensor K, is closed with empty interior. In general, the statements that I saw in the literature is saying that this set is generic. Well, it's nothing, it's just a proposition with empty interior. And the idea here, well, to prove that it's closed, it has nothing to do with theorem 2. you have just to use that every solvable group is meta-abelian. It's just this remark. You have just this well-known fact, no? But then you can prove that it is solvable. And to say that to see that it has empty interior, it's theorem 2. Because if I know that it's meta-abelian, then I can just construct something. Every group here is solvable. These groups are all solvable. But the point is that the range of solvability is essentially k plus 1 or something like that. So we can, on J4, I can construct a group which is solvable because it's here, but which has length 3. So we can obtain this proposition. And here, in fact, I could have stated, I know that is true also on C contained on a threefold, because there is a proposition of Fábio Brocheiro, another student of Camacho, which says that for G contained in GIF C2 0, then the range of solvability is at most 8. Okay. And then we could just repeat this statement, we could just say this on the threefold, and we think, I believe, well, Fábio believes, that this has nothing to do with C2. It's a general property of CM, no? And in fact, we could just state this proposition in general, even if we do not prove this theorem 2 for the general case, because for this C2, we can construct non-solvable groups just with the linear part, just with the linear holonomy. Okay? And I think that's everything I had to say. Thank you.
Thank you very much. So, question and comment? So, thanks again.
Yes.